Okay, thank you for introduction. So I'm now showing the whiteboard on yesterday's exercise session. So first of all, I want to correct the exercise session. Yesterday, I said that I am considered on yesterday's exercise session, I considered the Riemannian submersion. But I said that the Riemannian submersion can be, Riemannian submersion is taken such that Fi is not dependent on I, but it is not so. But after the talk, I was thinking again, and I realized that the following proof, we can prove the following argument. In the case of Fi also, Fi is depending on I, so we can argue in the case, also in the case of F is depending on I. So Fi may be dependent on I. Okay, this is the correction of my yesterday talk. Sorry for confusion. Then let me start today's session. On yesterday morning session, what I want to do is to state the spectral convergence results. This is yesterday's morning session's whiteboard. The spectral convergence means that if a sequence of Riemannian manifolds converging to some metric measure space in the sense of measured Gromov-Hausdorff topology and with some assumption, then their Laplace operator converges to the Laplace operator of the limit space. This is the spectral convergence theorem. And yesterday I have explained the definition of measured Gromov-Hausdorff topology. And today, first of all, I would like to explain the definition of this convergence. This is the convergence of spectral structure. To explain it, I use more abstract situation. So today, I want to explain about spectral structure and its convergence. First of all, I define the spectral structure. Let H and the pair of H and A is called spectral structure if H is an Hilbert space over C, and A is an operator on H, but A is an unbounded operator in general. So let dA be some dense subspace of H, not necessarily to be closed, and let A be the map, linear map from dA to H. This is linear, and I assume that it is self-adjoint and non-negative. So non-negative means that if non-negative means AU, inner product of AU and U is always non-negative for any u. Then the pair of H and A is called spectral structure. For example, let X and G be a Riemannian manifold. And let H be the space of L2 functions on X with respect to the measure mu G. Mu G is the Riemannian measure. And let A is the Laplacian given by G. Then the pair of H and A is a spectral structure. And this is a typical example. And Kuai and Shioya introduced the notion of convergence of them. They introduced two types of convergence. One is compact convergence, and the other is strong convergence of spectral structures, sequence of spectral structures. Now I'd like to explain these two definitions of convergence. First of all, let HI be sequence of Hilbert space. And we say HI converges to H infinity as I to infinity if there exists dense subspace of H infinity and there exists a linear map phi I from C to HI. This is linear map. And for such that for any U in C, the limit of the norm of phi I U with respect to the norm on HI converging to the norm of U. If this condition holds, then we say the Hilbert space HI converging to H infinity. So this notion of convergence depends on the choice of C and phi. So this convergence, depending on the choice of C and phi I, but for the simplicity, I omit this description, to write the dependence of these objects for the simplicity. Next, I want to define the convergence of the element of HIs. So next, let UI be an element of HI and assume that HI converges to H infinity. So then we have map phi I and subspace C associated with this convergence. And now we say that ui converging to u infinity strongly if there exists a sequence of a vector in C such that which converging to u infinity in h infinity, and we have limit k to infinity and limit sup I to infinity. Yes. Yes, please. Any question? Okay. Okay. So a limit k to infinity and limit sup I to infinity. Phi I u tilde k minus ui, and taking its norm on hi, then it converges to 0. By this condition, we define the strong convergence of the vectors.
I'm sorry, I didn't understood. Where is K in the definition?
K,
where is, what depends on K?
Okay, so
I see only I.
Okay, this is a sequence of C.
This is K.
Okay, yeah, this is K. So this is K.
Okay, okay, thank you.
Okay. And we also define the weak convergence. Ui converges to U infinity weakly if for every strongly converging sequence Vi, the limit of the inner product of Ui, Vi is U infinity, V infinity. If this equality holds for every strongly converging sequence, then Ui converges to U infinity weakly. Next, I'd like to define the convergence of spectral structures. Let Hi and Ai be the sequence of spectral structure. And we suppose that Hi converges to H infinity and put sigma I u epsilon I u, eiu is the inner product of aiu and u. Then the first notion of convergence is strong convergence. The spectral structure HIAI converging to H infinity A infinity strongly if for any weak convergent sequence, we have the inequality E infinity U infinity is not larger than limit infimum of EI UI. And there exists a strongly convergent sequence UI such that the limit sup of EIUI is not larger than E infinity U infinity. So in particular, by the first statement, first assertion, we can see that by combining these two inequality, we can say that if both of these condition holds, then this is equal. Sorry, this here is limit inf. This is the definition of strongly convergence. And I want to define one more convergence. HI-AI converging to H infinity infinity compactly if it converging strongly and for every sequence with this quantity is finite, the square norm of UI plus EI UI. The supremum of this quantity is finite. For such UI, there exists U infinity and there exists a subsequence of UI such that the subsequence strongly converging to U infinity. Then we say HI-AI converging to the limit compactly. So the compact convergence is the stronger condition than strong convergence. But this definition may be difficult to understand. So I'd like to explain what happens if these two types of converging holds. Let this is theorem by Kuwai and Shioya. Let HI-AI be the sequence of spectral structure. Now, assume that for any AI, all AI has compact resolvent. Yeah, compact resolvent, having compact resolvent means that this means there exists some complex number, zeta, such that zeta I is identity map, zeta I minus I, AI inverse is compact operator. For example, if AI is the Laplacian on the compact Riemannian manifold, then AI has compact resolvent. But in general, if AI is the Laplacian on non-compact Riemannian manifold, then this condition does not hold in general. Then I assume that HIAI converging to H infinity infinity compactly, the compact convergence occurs. Then we can say that there exists UIK in HI and K moves all positive integers, and there exists lambda ik, which is a non-negative real number, and such that here I moves, here I is in n or infinity, such that UIK is the eigenvalue, eigenvector of AI, and lambda ik is eigenvalue of AI. And UIK and moving K is a complete linear system, complete orthonormal system of HI. So HI is generated by UIK. And if we take the ring I to infinity, then lambda ik converges to lambda infinity k. And UIK converges to U infinity k. Here, this convergence is strong convergence. If this compact convergence holds, then we can take a basis of orthonormal basis, complete orthonormal basis of HI, and they converging to the orthonormal basis of the limit space. And we can also say the limit, the converging of eigenvalues. So compact convergence is very good convergence. Next, I assume that HIAI converging to H infinity, A infinity strongly. This convergence is weaker than compact convergence. Then, but in this case, we can also say that for any lambda in the spectrum of A infinity, there exists lambda I, which is a spectrum of AI, such that the limit of lambda I is lambda. So we may write, this implies that spectrum of A infinity is included in the limit of spectrum of AI.
Excuse me, there's a question in the
Yes.
There's a question in the
Okay.
separable.
What? Chat. Sorry. Oh, separable. So I'm not sure all of HI should be separable or not, but I think it is safety that we suppose that HI are separable. Sorry, I cannot answer explicitly.
Perhaps does the compact resolvent helps in this case?
Sorry?
You had an assumption that the resolvent of the AIs be compact. Would that solve the problem? But perhaps.
Example of what
In your hypothesis, you assume
yes.
that the operators had compact resolvent.
Yes, in the case of compact convergence.
Yeah. Does
Yes,
solve the
yes.
problem separability perhaps? But
so I cannot understand. Sorry, what is the question?
Maybe you just assumed that each of your Hilbert spaces has a Hilbert basis. And I think that implies separability, doesn't it?
So, okay. Yes. So, if I, so you say that if I assume that all of AI has compact resolvents, then HI should be separable.
Yeah, that's what Martin said, and I think you just said you had a complete orthonormal system, and that's counted.
Yes.
So the space is separable.
Okay. Yes. That's right. So in the case of one, yes. So HI should be separable. Yes, that's right. Thank you. Then, yeah, I'd like to show an example of spectral convergence, which converges strongly, but not converging compactly. This is a trivial example. Let H and H prime are Hilbert spaces. And let HI be the direct sum of H and H prime. So this is independent of I. And put H infinity is H. And let C is H infinity itself. And let phi I be the map from C to HI, and define phi I by x maps to x plus 0. 0 is the vector in H prime. So then we can show that HI converging to H infinity. And take any spectral structure on H and H prime. So these are the self-adjoint non-negative operator. And put AI is the direct sum of A plus A prime. This is also independent of I. And let A infinity be A. Then we can say that HI, AI converging strongly to H infinity, A infinity. But this is not compact converging if H prime and A prime is non-trivial. This is because for any xi, if we take xi from H prime in Hi, then the sequence xi has no limit, no strong limit in H infinity for any xi. So in this case, this is strong converging, but not compact convergence. Okay, then I go back to the, I want to go back to the case of Riemannian geometry. Let the metric measure space given by the Riemannian manifold, Riemannian metric GI, converging to some metric measure space X infinity, D infinity, mu infinity with respect to measured Gromov-Hausdorff topology. Put HI equal L to Xi nu GI. Then we have the convergence of Hilbert spaces as follows. To show the convergence of Hilbert space, we need C and phi I. So I have to explain how to take C and phi I. In this case, let C be the space of continuous function with compact support on X infinity. And this is a subspace of H infinity, and this is dense. And let phi I as a question. Any questions? Sorry. Okay. So let phi I be a linear map from C to HI. Phi I is given by the following. Now, recall that we assume that this measured Gromov-Hausdorff convergence And in the definition of measured Gromov-Hausdorff convergence, we have the approximation map. So let phi I be the approximation map from xi to x infinity. Associated with the measured Gromov-Hausdorff convergence. Then we put phi if. F is the compactly supported function, and phi if be the pullback by phi I. And if xi converging x infinity in the pointed sense, so pointed measured Gromov-Hausdorff convergence, then in this case, phi I is defined only on the open ball. Open ball. So in this case, we put phi if such that using the cutoff function, cutting off f. So phi if is the composition of f and phi I on the ball, and otherwise 0. Then we can define C and phi I, and we obtain the convergence of Hilbert space. And if xi converging to x infinity with respect to pointed measured Gromov-Hausdorff topology, and if the rich curvature of GI has uniform lower bound kappa, so there exists some real number kappa independent of I, and rich GI is not less than kappa GI, then on the limit space, we have a Laplace operator. This is a generalization of Laplacian on Riemannian manifolds. So we can define Laplace operator also on the metric measure space appearing as the limit of Riemannian manifolds. So this is by Chigakori. Then I can explain the statement of spectral convergence result. The first result of spectral convergence is obtained by Fryer. And later, Chigak and Colding shows in the weaker assumption. So first of all, I like to explain the Fryer's result. Let xi is an n-dimensional closed Riemannian manifold. This is closed Riemannian manifold of the same dimension. And let it converges. And we normalize the measure by the total measure. And suppose it converging to some metric measure space with respect to measured Gromov-Hausdorff topology. This is one of the assumption, and we need more assumption. Moreover, assume that the diameter of xi is bounded by some constant, and the sectional curvature is bounded by some constant. Then, of course, d and k is independent of y. Then this spectral structure converging to the spectral structure defined on the limit space. This convergence occurs. And this convergence is compact convergence. And later, this is the spectral convergence result by Fukaya. And later, Chiga and Colding showed that this type of theorem, by replacing the assumptions, the boundedness of sectional curvature by weaker assumption, they replace it by the lower bound, the existence of the lower bound of rich curvature. Then the same conclusion holds. Moreover, and this is the compact case. So all of xi are compact, and the diameter of xi are bounded.
I have a question here. So what if I take just a sequence of two tori, just a product of two circles, and one circle has fixed length, the other one shrinks to 0.
Yes.
Then I would get a measured Gromov-Hausdorff convergence here, just to isn't it?
So in this case, the limit is S1. Yes.
And you say you have compact convergence there, but now all
yes, it is compact convergence.
Otherwise, eigen values go to infinity in the limiting process. So I think this is only strong convergence.
Yes, but so I'm sorry. So in the sorry, maybe I had forgotten that. Here, so lambda ik means that the case eigenvalue so we ordering the eigenvalue from the smaller one. But sorry, I'm now confusing, so I cannot explain well. But I think the case you have mentioned is compact convergence, I think.
So you reorder the eigenvalues on
yes
free manifold, and then
yes.
Yeah,
so
sorry.
And I'd like to explain that one more spectral convergence obtained by Kwai and Shioya. They assume that xi, dgi, and mu gi and pi converging to some pointed metric measure space with respect to the pointed measured Gromov-Hausdorff topology, and suppose that they assume only the existence of lower bound of Ricci curvatures. So they do not assume the compactness of xi and the boundness of diameter. Then in this case, we can also obtain the convergence of spectral structure in the sense of strong convergence. And in my talk, in our case, we want to apply these results to the situation of geometric quantization. And if we apply these results to our case, then our family of metrics given by the omega compatible complex structure is that there are no upper bound of diameters. So we use the Kwai-Shioya's convergence result. Now, we consider the sequence of pointed metric measure space and assume that S1 action on this space is given. And this S1 action preserving metric and measures. Then we define that this sequence converging to the limit. Of course, limit also has the S1 action with respect to S1 equivalent pointed measured Gromov-Hausdorff topology. If this is the pointed measured Gromov-Hausdorff topology, and in the definition of pointed measured Gromov-Hausdorff topology, we have the approximation map phi I, and we assume that phi I is S1 equivalent. Then if we have this, then we say that this sequence converging to the limit in the sense of S1 PMGH. This is not so difficult. Let Sy dgi hat mu gi hat with some normalization and pi converging to some limit space with S function. here GI hat is a Riemannian metric on SI. So I suppose that SI is Riemannian manifold with isometric S1 action, and G hat I is the Riemannian metric. And so we have S1 action. And this convergence is S1 PMGH. This is assumption. And moreover, we assume that there exists some real number kappa such that the Ricci curvature of GI hat is not less than kappa GI. So the uniform lower bound of Ricci GI hat exists. And this is also assumption. Then we have this spectral structure L2SY tensor C, and taking the invariant subspace with respect to the action rho k, and we have the Laplacian GI hat with acting on the invariant space. Then it's converging to we can regard this as spectral structure, and then it converging to L2 S infinity tensor C, and taking the invariant subspace and the limit of the Laplacian on the limit space. And this convergence is the strong convergence because we do not assume the upper bound of we do not assume the existence of the upper bound of diameters. So this is strong convergence. And this proposition is shown by Kuai-Shioya's this theorem. Applying this theorem to the case of Xi has S1 action, then we get this proposition. So we want to apply this proposition to our situation. And to apply it, we suppose that when we apply this, we suppose GI hat is GJS hat. GJS hat is the connection metric given by GJ and the S1 connection on S in the case of geometric quantization. So in this case, we need the assumption of Ricci curvature. So we have to compute the Ricci curvature of GI hat. So in particular, in the case of geometric quantization, we need the lower bound of the G hat JS. But it can be computed if S is the unit circle bundle of LH. LH is the prequantum bundle on X and omega, and let G hat is G hat J, and this is a connection metric and given by the connection S1 connection A and the base metric Gj. Then we can compute Ricci curvature of G hat J as this. Ricci of Gj minus Gj over 2, 0, 0, n over 2. And this decomposition is here. This is so the tangent space of S is decomposed into the horizontal space and the fiber-wise tangent space. So the tangent space of fiber, and the fiber is one-dimensional in this case. And this is the fiber, and this is the base or horizontal direction. So to obtain the lower bound of reach of G hat J, it suffices to obtain the lower bound of the base metric. So if we have lower bound of the reach curvature of Gj, then we obtain that of the connection metric. This is the story. So, okay. So I have 3 minutes, but okay, I stop here today. Thank you.
Thank you very much for your talk. Are there any questions from Freiburg or from online?
I have one question.
Yes.
You assume, I don't know whether you assume the integrability for JS or the integrability of JS is a consequence. Is it a consequence or assumption? Integrability of JS.
Yes. In fact, the integrability of JS is not so essential. So yeah. In fact, we can prove this story without integrability.
Without integrability.
Yes.
But,
okay. Yes.
So you don't need Kähler geometry.
Yes, but one point is that so what is our main concern is to study the space of holomorphic section. So to define holomorphic section, the space of holomorphic section, then we need the integrability of J. So, but without it, to study the analysis, we do not need integrability.
You can use, for instance, the Dirac operator or something like that.
Yes.
Yeah. Thank you.
Any more questions, comments? No questions from Freiburg, from online? Okay, it doesn't seem to be the case. Then we can thank our speaker again. Thank you very much.
Thank you.
And I will stop the recording.